Section. Introduction. In simpler terms, we're discussing how large language models, LLMs, can solve complex reasoning problems more accurately when they're guided to work out the answer step by step. This process, often referred to as a chain of thought or scratchpad method, encourages the model to generate a rationale or a sequence of reasoning steps that lead to an answer. This seems to be easier for the model than generating the final answer directly. Despite the effectiveness of these methods, there are still instances where the rationales produced are incorrect. One way to improve this is by fine-tuning the models to generate better rationales. This can be done if we have access to high-quality rationales, which can be obtained through crowdsourcing or automated methods. However, getting this data can be challenging. An alternative approach is to start with datasets that only contain questions and correct answers, which are more readily available, and then generate rationales during the learning process. A version of this strategy was proposed as the self-taught reasoner, STAR, which generates proposed rationales from an LLM, and then fine-tunes on rationales that lead to the correct answer. In this paper, we're taking a different approach to generating rationales. We're viewing chain-of-thought methods as probabilistic latent variable models. The LLM defines a joint probability distribution over questions, rationales, and answers. This joint distribution implies a marginal distribution of answers given questions, averaging over all possible rationales weighted by their probability given the question. The problem of self-training for reasoning then becomes one of learning with incomplete data, a core task in probabilistic machine learning. This perspective raises a technical challenge, because computing the marginal distribution requires averaging over a vast set of potential rationales. To address this, we introduce a learning algorithm for rationale generation, which we call TRICE. TRICE is a simple Markov-chain Monte Carlo, MCMC, expectation maximization, M, algorithm combined with a novel control variate scheme. This view unifies several threads of work in reasoning using LLMs. It provides an alternative interpretation of STAR as a kind of biased stochastic expectation maximization algorithm that underweights difficult examples when its rationalization process fails. Compared to STAR, TRICE is less likely to ignore difficult examples, which stabilizes convergence and improves performance, and is also able to learn from incorrect rationales as well as correct ones. We apply our technique to the GSM-8K dataset and to the Big Bench hard benchmark. We find that TRICE improves the model's performance significantly, outperforming models tuned with STAR, direct tuning with or without COT, and even supervised fine-tuning on human-generated rationales. In terms of method, given a training set of n questions and answers, we formalize COT tuning as optimizing a parameter vector to maximize the average marginal log likelihood of answers given questions. We're particularly interested in models where the likelihood, that is, where the answer is a deterministic function of the rationale. For example, we might say that the model's answer is A. If the rationale ends with the string, the answer is A. We believe that such a binary likelihood model is appropriate for question answering tasks where the rationale is a good rationale should leave no ambiguity about the correct answer. The derivations below will therefore assume a binary likelihood function. It is straightforward to generalize our methods to cases where the relationship between the rationale and the answer is weaker and therefore the likelihood is more complicated. We start by initializing a memory containing a latent rationale for each example pair by sampling from a hinted guide distribution that may condition on the correct answer as well as the question. For example, the guide might prompt an LLM specifically to give a rationale for the answer. In some cases, sampling from the guide instead of the model increases the chances of generating a correct rationale. We then proceed to the main optimization loop. Each iteration, we sample a mini-batch of questions and answers from the dataset, and retrieve the rationales associated with those examples from the memory. We then propose new rationales from the current model, and whenever the new rationale is correct, replace the old rationale in memory with the new one. At this point, we have all we need to compute a gradient estimate. We can just average the gradients that we obtain from those rationales in the updated memory that are correct. But we can also reduce the variance of our gradient estimator by incorporating a control variate. We first compute leave-one-out estimates of the average probability of accepting a new rationale. For each example, we subtract off a scaled control variate whose expected value is 0. If the proposed rationale, for example, is correct, then the gradient contribution becomes scaled down. If the proposed rationale is incorrect, then we adjust the gradient estimate to try to make the proposed rationale less likely under the model. As the model becomes more accurate, we give more weight to incorrect rationales when they occur, and less weight to correct rationales most of the time. This method is more expensive than the basic gradient estimate, since we must compute gradients not only for the rationales in memory but also for any incorrect rationales we generate. To reduce this cost, we use resampling to generate a subsample of question rationale pairs, from which we obtain an unbiased estimate of the output of the control variate gradient estimate. We preferentially sample gradients with higher scalar weights. This can be seen as a generalization of the strategy for reducing the cost of computing gradients. In the following sections, we'll delve into this variance-reduced stochastic MCMCM procedure in more detail. Section Summary. In this section, the authors introduce a learning algorithm called TRICE for generating rationales in chain-of-thought methods. TRICE is a Markov-chain Monte Carlo (MCMC) expectation maximization (M) algorithm that improves the model's performance by averaging over rationales during training. This approach allows TRICE to learn from both correct and incorrect rationales, making it more effective than previous methods such as STAR. Section. Derivation. Let's break down the complex concepts in the given text. Firstly, we're looking at the gradient of the marginal log likelihood, which is a measure of how likely our model's parameters are given the data we have. This gradient is the expected value of the gradient of the conditional log prior, given the posterior distribution. The posterior distribution is the probability of our model's parameters given the data. If we can sample from this posterior distribution, we can estimate the gradient of the marginal log likelihood. This process is like creating rationales that align with both our prior beliefs and the observed data. However, we can't directly sample from the posterior distribution, so we use a method called Markov-chain Monte Carlo, MCMC. This method involves keeping a record of a single rationale for each data point, and at each step, we randomly update this rationale in a way that doesn't change the posterior distribution. Each update brings us closer to the true posterior distribution. But, when we update our model's parameters, the posterior distribution changes, so we need to keep updating our rationales to control the bias in our gradient estimates. To update our rationales, we use a simple method called an independent sampler. This method proposes a new state and accepts it with a certain probability. If the proposed state is correct, we accept it, and if not, we reject it. This method can be seen as a way to generate and evaluate proposals over time. If we fail to sample from the posterior distribution, we fall back on an old sample. The number of iterations between successful updates is inversely proportional to the probability of the data given the model's parameters, so the process is faster for easier data points and speeds up as the model improves. This MCMC method allows us to approximate the gradient of the marginal log likelihood. We sample a proposal, accept it if it's correct, and compute the gradient of the log probability of the result. The estimate will have low bias if the distribution of the updated state is close to the posterior distribution, which is likely if the chain is mixing quickly enough relative to how fast the model's parameters are changing. This will happen if either the probability of getting a correct answer is high, or if the model's parameters are changing slowly due to a small learning rate and/or gradient. If the model's accuracy improves with training and we use a decaying learning rate schedule, then as training proceeds, both of these factors should work to reduce the bias of the gradient estimate. Section Summary. The gradient of the marginal log likelihood with respect to theta can be computed by sampling from the posterior over rationales conditioned on the question-answer pair. Markov-chain Monte Carlo, MCMC, is used to update the chains and control the bias of the gradient estimates. The estimate will have low bias if the distribution of the proposal is close to the posterior, which can be achieved by a high probability of getting a correct answer or a slow change in theta. Section. Adding a control variate. Let's simplify the given text. We're discussing the concept of adding a control variate. The average of an estimator, which we'll call g hat, doesn't change if we subtract a random variable b with zero mean from it. If b is positively related to g hat, then g hat minus b can have a lower variability than g hat. In this case, we can use b as a control variate. According to the score function identity, the expected value of beta times the gradient of theta log p underscore theta, z given x, equals 0. Here, beta is any scalar that doesn't depend on z. We can use the proposed samples, z tilde, to generate control variates for our gradient estimator. The value of this estimator depends on whether we accept the proposal, z tilde. We use c tilde as a shorthand for c, z tilde, y. This control variate can reduce the variance of the gradient estimator to 0 as the model becomes perfectly accurate on the training set. If we set beta equal to pi, where pi is the probability of a correct answer, meaning c tilde equals 1, then as pi increases, most of the time, c tilde equals 1 and we multiply our gradient estimator by 1 minus pi. This multiplies its variance by a factor of 1 minus pi squared. If c tilde equals 0, we use both a correct and incorrect rationale. The weights attached to these updates won't be small, but if incorrect rationales are relatively rare, their contribution to the variance of the gradient estimator will be small. If the model hasn't yet learned to frequently generate good rationales for the training examples, we should set beta closer to 0. In this case, the signal from the incorrect rationale is less informative. We show that the variance of gradient estimators based on incorrect rationales strongly depends on the model's accuracy, pi. We also show that choosing beta equals pi is optimal up to 1 minus pi squared terms, and that the variance of the resulting estimator is proportional to 1 minus pi. For each example, x_m, y_m, we need to compute a beta_m that approximates the expected value of c tilde_m in a way that ensures that beta_m is independent of the gradient of theta log p_theta, z tilde_m given x_m. We assume that the expected value of c tilde_m is approximately equal to the average acceptance probability across the mini-batch. We compute the leave one out estimate, beta_m, as the sum of c'_m times c tilde'_m over the sum of c'_m, where c'_m equals c, z'_m, y. We only consider examples for which we have a correct rationale, where c'_m equals 1, as these are the only examples that influence our gradient estimate. Leaving out c tilde_m and c'_m from the estimate, beta_m, ensures that beta_m is independent of z tilde_m. We can reduce the cost of our gradient estimator by using resampling to select a subset of rationales. This doesn't affect the expected value of the estimator as long as the probability of selecting a rationale is proportional to the corresponding weight, w tilde_m, and the averaged gradient is reweighted by the sum of w tilde_m over the sum of c'_m. We considered three alternatives to the MCMCM approach that we use in this paper: variational M, reweighted wake sleep, and rejection sampling. Variational M is a common strategy for training latent variable models, but it's challenging with discrete latent variables. Reweighted wake sleep is an attractive alternative that avoids high variance score function gradients. However, we found that it sometimes led to degenerate zero-length rationales. Longer sequences tend to get lower weights, so the model and guide learn to produce shorter and shorter sequences until they consistently produce empty rationales. With careful initialization and learning rate tuning, we could sometimes get reweighted wake sleep to avoid this problem. But this led to a new problem. The guide model learned to closely mimic the prior until the very end of the rationale, and then simply paste in the correct answer whether or not it had anything to do with the rationale up to that point. Finally, we considered a rejection sampling scheme in which we sample proposal rationales from p, z given x, and average the gradients from those rationales that lead to correct answers. While this scheme can work, it requires reducing the mini-batch size by a factor of k to keep the per iteration cost constant compared to trice, which in turn leads to slower convergence and/or worse final results. Section summary. Adding a control variate involves subtracting a zero-mean random variable from an estimator, which does not affect its mean. If the random variable is positively correlated with the estimator, the resulting estimator can have lower variance. In this paper, the proposed samples are used as control variates for the gradient estimator, which can drive the variance of the estimator to 0 as the model improves its accuracy on the training set. Section. Related work. In the field of neural sequence models for problem-solving tasks, various methods have been proposed for generating rationales. These methods range from fully supervised to few-shot approaches. One method that is particularly relevant to our work is the self-consistent chain of thought. This method can be seen as a way to consider different rationales when testing. It has been successfully used in various quantitative reasoning tasks. However, there are fewer methods that use imputation or averaging over rationales during training. One notable example is the star method, which we will discuss later. Some researchers have suggested representing a composition of language model interactions through probabilistic programming. We have been inspired by this work and treat rationales as hidden variables in our approach. There are other examples of interpreting language logic models with chain of thought as hidden variable models. Variational inference and wake-sleep methods are commonly used in the hidden variable modeling community. However, we found that the bias of these methods can cause serious problems. MCMCM, a less common strategy, has been widely used to train undirected graphical models. Our method, TRICE, can also be seen as a type of Markovian score climbing. The REACT method showed that incorporating reasoning into an observe and act loop can significantly improve performance. This method was further developed in reflection, where an agent can reflect on a trajectory, enhancing the resulting examples for use in future rollouts. These methods have shown significant improvements in their respective evaluation tasks. However, they still rely on the model's ability to provide useful feedback through few-shot prompting. In contrast, our method actively adjusts the model to produce thoughts that are beneficial to the task. Recent work on tool use within language models also uses imputation to determine where to insert calls to tools. Their loss functions are similar to ours, filtering out trajectories that do not lead to valid answers. In our paper, we treat rationales as hidden variables, but one could also treat tool use as a hidden variable. The most closely related work to ours is the self-taught reasoner, STAR. There are three significant differences between TRICE and STAR. First, STAR uses greedy decoding, which limits the diversity of the rationales it trains on. This choice was made to reduce the risk of the model providing the correct answer despite having a poor rationale. While we have found that our procedure sometimes produces correct answers for the wrong reasons, this did not seem to hinder the model's improvement on most tasks. One reason for this could be that our base models are more powerful than the GPTJ model used in the STAR paper, making them more likely to generate good rationales from the start. Secondly, TRICE resamples rationales every iteration, reducing the likelihood of overfitting to any particular rationale. STAR, on the other hand, runs many training iterations on a single set of rationales, which can lead to the model effectively memorizing a fixed set of rationales for the training set. Lastly, when STAR updates its rationales, it may replace a rationale from the model with a rationale from a surrogate. As the model memorizes a set of correct rationales for the training set, STAR becomes less likely to fall back on the surrogate, but this choice could affect early training dynamics. Section Summary. Several methods have been proposed for generating rationales in neural sequence models, including self-consistent chain of thought and STAR. However, our approach differs from STAR in several ways. We use resampling of rationales to avoid overfitting, our base models are more powerful, and we maximize log likelihoods instead of likelihoods to prevent the model from giving up on difficult questions. Section. Experiments. In our experiments, we tested TRICE on two datasets, GSM-8K and the 27 Big Benched Hard (BBH) tasks. We used a medium-sized transformer-based language model called POM2M. For the BBH tasks, we used a version of POM2 that was tuned for flawn instructions, while for GSM-8K, we used the base model of POM2, as GSM-8K is part of the flawn training datasets. All our experiments were conducted on TPU v4 and v5e chips. Instead of fine-tuning the model weights, we used a method called prompt tuning. This involves adding a sequence of embedding vectors, which we refer to as a soft prompt, to the embeddings that correspond to the tokenized COT prompt used to condition the model. This method can achieve similar accuracy gains to full fine-tuning, but with fewer parameters. We initialize the soft prompt with the embedding sequence obtained from a series of 3, for BBH, or 5, for GSM-8K, exemplar COT prompts. Each prompt was in the form of a question and answer, with a rationale for the answer. We considered two initialization schemes, one using standard few-shot COT prompts provided with BBH, and another where we tried to bootstrap a few-shot COT prompt by randomly sampling questions from the training set, generating random rationales from the base model. and picking examples where the random rationales led to correct answers. For each BBH task, we divided the examples into 60% for training and 40% for testing. For GSM-8K, we used the standard training set of 7,473 examples and a test set of 1,319 examples. We evaluated the accuracy of COT models in two ways. First, using greedy decoding, and second, using a method called self-consistency. In self-consistency evaluation, we drew 40 samples and checked whether the most common answer was correct. We compared TRICE against 4 baseline prompt tuning methods: direct prompt tuning, COT prompt tuning, rejection sampling, and STAR. All methods were evaluated against the same validation sets and used the same training labels, few shot prompts, and initialization strategies as appropriate. Our results showed that even without human-generated exemplar rationales, TRICE was able to learn to generate rationales that led to the correct answer. TRICE also outperformed a model trained directly on human-generated rationales on GSM-8K. This could be because the loss used in supervised fine-tuning may place more weight on style than substance. By the end of training, TRICE had managed to generate at least one valid rationale for almost all training examples, while STAR failed to generate valid rationales for almost 10% of training examples. Unlike in the experiments done on Common Sense QA, STAR did not outperform the direct prompted prompt-tuned model on BBH. This could be because each BBH task includes relatively little training data, and so STAR overfits to its relatively small set of bootstrapped rationales. TRICE, on the other hand, can overfit to the small set of questions but at least has a chance to generate a somewhat diverse set of rationales from those questions. In conclusion, our experiments showed that TRICE converges to high training accuracy much faster than rejection sampling, particularly towards the end of training as the probability of generating correct answers on the training set increases. Section Summary. The TRICE model is evaluated on the GSM-8K dataset and the 27 Big Bench Hard BBH tasks using the POM2M transformer-based LLM. Prompt tuning is used instead of fine-tuning the model weights, where a soft prompt is prepended to the embeddings. TRICE outperforms other prompt tuning methods and even a model trained directly on human-generated rationales, demonstrating its ability to generate valid rationales and achieve high training accuracy. Section. Discussion. In our discussion, we introduced TRICE, a technique designed to enhance the performance of large language models, LLMs, in question-answering tasks through a method known as chain of thought, COT, prompting. We conceptualized the COT-prompted LLM as a model with hidden variables, which allowed us to develop a systematic and efficient fine-tuning method. When tested on tasks from GSM-8K and Big Bench Hard, BBH, TRICE surpassed 3 robust benchmarks: direct prompt tuning, STAR, and rejection sampling. Although we developed TRICE specifically for COT question answering, its core strategy, based on the Markov-chain Monte Carlo expectation maximization (MCMCM) method, could be applied to a wider range of problems, such as those involving tool use. However, our method has some limitations. We only tested TRICE with prompt tuning on a medium-sized LLM, so its performance on smaller or larger models, or with other fine-tuning strategies, remains unknown. TRICE relies on gradient-based tuning, but many of the most advanced LLMs are proprietary, and their owners often do not offer public access to gradient-based fine-tuning tools. This makes it challenging to assess how well TRICE would perform with, for instance, GPT-4. Additionally, our quantitative evaluations mainly focused on whether the LLM could generate the correct answer, without formally assessing the quality of the reasoning in the rationales themselves. In terms of broader impacts, our work aims to enhance the capabilities of LLMs, making them more accurate and transparent in answering questions. However, there are potential downsides. More capable LLMs could be misused or used unsafely. Fine-tuning on unfiltered question-answering datasets could introduce biases into the models, and the increased use of LLMs could lead to a larger carbon footprint. Rationales might make it easier for discerning users to evaluate the reliability of LLM outputs. However, many users might not scrutinize an LLM's rationales, accepting the mere presence of a rationale as proof of truth. If chain-of-thought rationales encourage uncritical trust, they could potentially cause harm. We would like to express our gratitude to Daniel Freeman and Enrique Piqueras for their contributions to the infrastructure we used in our experiments. We also appreciate the valuable discussions we had with Kevin Murphy, Ben Lee, Brian Patton, and Yasha Sol Dickstein.